Hi, I'm Steve Saffel and this is a video to help the HND students analyse the data for the power test experiment. This is assignment 1. Okay, so what this assignment is about is looking to see if there are cheaper alternatives to the Wingate power test. What we have here is a Wingate bike. This costs about £4,000. If you add on things like a laptop, then you're looking at about £5,000. Also, it's quite restricted as to where you can do it. For example, it's big, it's heavy, so it belongs in a lab. If you're going to be testing people, then you have to take them to the lab rather than you take the test to the people out in the field. There are two alternative tests that we can do. These are the Margarita stair test and the sergeant jump. The Margarita stair test basically needs a flight of stairs that you run up and you time how long it takes. Other things you need are a tape measure. The sergeant jump is even cheaper and more simple. All you need is a wall and a bit of chalk and measuring tape at the minimum. All you need to do is measure how high somebody can jump. But the big question is, are these tests comparable? They all measure power in their own different way, but the question is, can we save a lot of money and a lot of heartache taking people to the lab by doing these experiments out in the field with the resources that we normally have? So, the hypothesis that we will be testing is all three tests are comparable, or in other words, statistically, there is a significant correlation between the sergeant jump, the Margarita stair test, and the Wingate peak power test. And of course, the null hypothesis is there will be no correlation. Or in other words, what we're saying here is if you're good in sergeant jump, you might not be good in the Margarita stair test, and so on. So, testing. First of all, we collected anthropometrical data to see if everyone was in the normal population. This included things like height, or stature as it should be called. We have the body mass, and then we did the tests. Of course, with the sergeant jump, instead of using chalk and a wall, we used a jump mat called Just Jump, because that's what you basically do, and it tells you how high you jumped in centimetres. The other test was the Margarita stair test, and we used a flight of stairs within Vaudeville, and then of course we used the lab-based one, which was the classic Wingate power test, lasts for 30 seconds, but all we did here was we just measured the peak power, which is the first 10 seconds. So once we got the results, what we did was we put it all into an Excel spreadsheet, and what we're going to do is we're going to be looking at different aspects of this data. For example, in the grey area here, what we have is the anthropometrical data, basically kind of stating what kind of person did the test. So we've got variable factors such as sex, age, stature and body mass. Note that we use the term stature rather than height, because height can mean how tall you are when sat down or in different positions, whereas stature is your normal height, or in other words, how tall are you when you stand up normally. And then body mass. We use that instead of weight because there are differences in weight. The extreme example is, of course, if we weigh ourselves on the moon, we're a lot lighter, but we're still the same amount of matter. Body mass. And so we use the term body mass instead because it's a better term to use. In the light blue here, what we have are the results for the sergeant jump test, and what we have here in the white are just our initial times. From the initial times we did a simple calculation, which is your body mass multiplied by 9.8, which is acceleration due to gravity, times 1.8, which was the height of the staircase, divided by how long it took you. And from there we can work out your power. And then what we did then was we converted that from watts into watts per kilogram of your body mass. So 890 divided by 65 will give you this value here. The last two columns here, the other one in the white is your peak power value. The peak power value is measured in watts, so what we've done once again is converted into watts per kilogram. Why we convert it into watts per kilogram is simply that in a lot of kind of sports, your body mass is important. It's a lot of agility work. So if you are of a heavier type, then it's harder for you to kind of accelerate, change direction, jump and so on. So body mass is quite important. So we've done that for both, and that's how it is for that. And we will be using the watts per kilogram values for these two to do our comparisons later on. So what descriptive things can we do in Excel? Well, first of all, what we could do is we can summarize the anthropometrical data. So question 1 is how many males and females. Of course, you can just get your fingers out and count them, but might as well do it a smarter way, just in case you extrapolate this to include thousands. What you can do is you click onto formulas, auto sum, and in here what I'm going to use is a function called countif. So if I search for that, there it is. If I click on there, and it asks for the range, and the range is all the values in this column here, and the criteria that we're going to use is, I use the code M for male, so I'll just stick in an M, and if I click on there, then we've got 12. And of course what I can do is just drag this little box down there. There were 22 subjects. Out of those 22 subjects, 12 were male, 10 were female. That's a nice little summary. For the rest of them, what we're going to do is work out the means and standard deviations. So the same thing, if I click on auto sum, what I can do is click on average, ask me for what range, and I'm going to say all this lot here. That's it. Click and enter, and there's our value, 20.23 average or mean age. And what I'm also going to do is measure standard deviation. So if I just click on there, type in standard deviation, it comes up with all these lot, and stdev is the one that I actually need. So just click on that, ask me for the range again, so it'll be that lot over there, stick on that, press enter, and there we have the value. So the mean age was 20.23 years, plus or minus 4.16 standard deviation. Now if I just highlight those two, see the little bottom right box, drag that over, and it will work it out for all the rest of them. I'll just get rid of the ones that we don't need, which are these here. So there we go. What we have here is simple descriptive statistics for the data we've got. So we can say that there were 12 males and 10 females. Question is, we use these descriptive statistics to work out whether our sample of 22 people would best represent the general population. And as we all know, the ratio of males to females is roughly 50-50, and 12 to 10 is pretty close to 50-50 anyway. So for the ease of this research project, we're going to say that yes, that's a fair distribution there. Now of course, when it comes to things like age, stature, body mass, then yeah, we've got the means and the standard deviation. So the mean age was 20.23 years old, plus or minus 4.16. Interestingly, if you look at that, what that is saying is mean 20.23, and the majority of people are between 16 and 24. But we have to remember that, well, the youngest person that did this test was 18, so already there might be a little bit of skewedness into this data, especially if we consider subject CS, but her age is 37 years old, and of course being 37 compared to all the rest of them, it does look like that will skew that, and the data on Excel doesn't really kind of show that, so we'll look into that later on. Also on there we've got the mean stature was 1.73 meters, plus or minus 0.08, which is pretty standard as far as I can remember, and also there is a greater range of body mass, so 76 plus or minus 17.48, so that shows a wide range of body masses from the very light person to the more stockily built person. And then lastly, what we got here is the actual test that we did. So we've got sergeant jump mean score of 48.77 with your standard deviation, but you can't really compare that with the other test because this one here measured in centimeters and these are measured in watts per kilogram. So what we could do is data as headers, so that means I can sort it by sergeant jump, go from the lowest score to there. So one way we can do is simply have a look at, well, they scored low in here. Looking at this, yeah, they did score low on there. There is a couple of different ones, like subject NF got a pretty good sergeant jump score, but not a comparably good one in the Margarita. Funnily enough, the same thing happened in the Wingate, so that was maybe they're trained to jump or something like that, but not trained to run up flights of stairs or go on a bike. But you can see there is a general tendency that if there is a low score in the sergeant jump, then there will be a general tendency to score a low score in the Margarita, and the Wingate. Of course, if we're going to be comparing the Margarita test and the Wingate test, it's a little bit easier because what we have are the same units of measurement here, so watts per kilogram for both. And if we have a look at the mean scores, then the mean score for the Margarita was 14.71 plus or minus 2.79, and Wingate 13.58 plus or minus 2.66. So what we can say there is, yeah, there does seem to be a difference. There's a difference of what, 1.13. So 1.13 watts per kilogram. So they are kind of roughly in the same ballpark, but 1.13 might be a big difference. So they might not be measuring the same value as such. The Margarita stare test seems to be measuring above what the Wingate test does. But of course this data here does show there is a difference. The question is it a significant difference? Can we say that yes, every time we do the Margarita stare test, we'll always get a measurement that is higher than the Wingate power test? It doesn't show in this. What we need to do is think of different ways of looking at these values. So what we can do is we can use an amazing package called SPSS. There is a little bit of setting up that you need to do to make the data as usable as possible. You may notice that, for example, here sex is no longer M&F for male and female. I've coded it as 0 for female and 1 for male. This is because it gives us a little bit more flexibility when it comes to analysing the data. Computers prefer it coded like this, and it doesn't matter too much when there are 22 subjects here that we're analysing, but SPSS is better designed for thousands and thousands, so if we coded it M&F it can slow the whole thing down. And also it's also to do with the size of the numbers that you got here. The less numbers the better. I can explain this a little bit better if we look in the variable view. Here what we got are the different columns. So of course in the first column we've got what we're going to call it, so what we had in Excel, which is ID, sex, age, stature and so on. The second column here is what kind of variable is in there. So the first two are strings, which are just basically, they're not numerical or measured values. They are, for example here, the ID, which is letters, and sex is just a code for 0 and 1 as to what it is, but it isn't an actual measurement. 0 isn't a measurement of being female, and 1, it's just a code. And this is also indicated here at the very end where it says measure. So we have ordinal, nominal, we can also have scales, but these are nominals. We use the term nominal as a measure because they're basically labels. We're labeling people, so the ID is a person's label. We use subject CS with her age, it's 37. She may be classed as an outlier because not everyone else is in that age. She's way out there as far as age goes. We can easily do that, so we call that a nominal, a label, and then sex of course is labeling people either male or female. The rest of the values here in measure are all scales, or in other words something that we measure. As I say, what we try and do is keep the column width as small as possible, so I could do, if I wanted to, make this like 20 long so we can put in full names. But what you will find is if we do experiments with thousands of people, the longer the strings are here, then the slower is the analysis process. So we keep it short and sweet as much as is possible, and of course we add how many decimal places we need to do there, and that should keep it all quite quick when it comes to analysis. The label column just helps you identify or give you a better description than in the name. This is short and sweet. The label column can give you a little bit more. So what I've done here is just remind myself that 0 is female, 1 is male. And another simple thing I always do is I try and put in the units of measurement in here. You'll be amazed how many times people do errors where instead of using watts, they'd be measuring in kilowatts, and so all the results are completely wrong. When it came to sex, male, female, what you need to do is identify that 0 is that, and this is in this box here. So if I click here, what you notice is if I put, I'll just put in a random other one. So if I put in a value 2, that is somebody that has not stated what they are. So just click on that and you can do that, and as you can see it just creates that. So when I code it, they know which it is, but of course we don't need that one, so I'll just take that one out, and that is a coding 0 female, 1 male. And that is the majority of the setting up that we need to do. So back to the data view, this is the data that we're going to be analysing. So the hypothesis that we were testing is looking to see if there's any links between Sergeant Jump, Margarita stare, Wingate peak power. So can we use SPSS to do that? Well, of course we can. But first of all, Question number 1 is always, is our data parametric? So what we need to do is do a quick analysis. You may remember from lessons we have made a few graphs where we're trying to make normal bell-shaped data. So we get lots of data, stick them in histograms, and hopefully you can get that. This SPSS can do that, and it can do a little bit more to help you identify whether data is normal. So if I click on Analyze and go to Descriptive Statistics, there's lots of different options here. Normally you could put on descriptives and it'll give you your mean, standard deviation, ketotic score, skewness score, all the things that we talked about. But if I click on Explore, it can give us a little bit more. So on here, what I'm going to do is, first of all, I'm going to identify all the anthropometrical data, which is age, stature and mass. We'll see if that's normal, and just for fun we'll see whether the Margarita stair whether the sergeant jump, the Margarita stair test and the Wingate are normal distributions as well, so I'll stick them in as well. If I wanted to, I could also separate it, so just compare all the female data alone and all the male data, but I'm going to chuck you all in together and see what happens. Now in these boxes here, if I click on statistics, I'll just see what's ticked. So we're going to use a descriptive statistics, confidence level 95%, which basically means if we did this test 100 times, 95 out of the 100 will get exactly the same results as we will do today. So I'll click on that and I'll just check plots. I'll click on histograms, seeing as that's what we've been doing more of rather than stem and leaves. And also I'm going to tick on this box here, normality plots with tests, and what this is, it will give us a number to say whether the data is normal or not. And what we can then do is compare the histograms and the actual statistical values and to decide whether the data we're analysing is normal. So I'll click on OK there, and here are the results. So the first box here is just giving you an overview. So there was 22 participants and we've got 22 values in all of those that we've analysed. There's none missing, and so everything is all happy and hunky-dory. We haven't made any erroneous mistakes anywhere. So as with Excel, what it can do is, for example, age, give us our age, and in there is also our standard deviation, so 20.23 plus or minus 4.163. But also, as I say, it can give you other values, min, max, the range in between, and all this. This all helps us work out whether the data is normal. If I go to the histogram, so I'll click on histogram for age. Remember making these, what we're after is a nice bell shape as such. And if we look at age, you may notice that it's kind of that standard normal shape, but we have that subject CS all the way over here that is skewing the data as well. So would you be happy calling that normal? It's hard to say. There's 22 subjects, so you'll never get a perfect bell shape, but we can't do, and that's where we can do other tests. So if I go to tests of normality, what we have here is 2 statistical tests of normality. One is the Kolmogorov-Smirnov test, or the KS test we'll call it, and then the other one is the Shapiro-Wilk, or the SW test. And what these do is it works out whether they are normal or not. The key values here are the SIGs. Kolmogorov-Smirnov we hardly ever use. They're best used for sample sizes of more than, say, 2,000-3,000 subjects, but we've only got 22. The Shapiro-Wilk is best for us, so most sporting examples that you will ever use would use the Shapiro-Wilk. What we're looking for is a SIG value. If it is more than 0.05, then we can say that actually the data is normal. So if it's beneath that, it's not normal. So age is beneath 0.05, so that is not normal. For the rest of them, they are above it, so they are normal. So when we write about it, we can say the data was deemed normal statistically as far as the Shapiro-Wilk goes, apart from age. And of course we know why, basically because all our subjects were undergraduate students at a university, and people that are between 18 and 21, say, don't kind of best represent the whole population of the world. So it's very, as you can see, the majority of people are in this area here, not the whole range across there. So age isn't normal, so we might have to change the title of the experiment to comparing power tests for undergraduate students, which would then kind of say we've taken this into account, or we just kind of start analysing and testing more people of various ages. But as I say, the rest of them, they all look pretty normal. And if we look at the histograms for the others, so for example with mass, you can see there it's getting more bell shaped here, so we're happy with that. For the sergeant jump, yep, you can see a slight bell shape. For the Margarita, there it is, can't get any better than that. And the Wingate, That's pretty good as well. So yes, visually, using histogram, they look normal, and statistically, using the Shapiro wheel, they are normal, all apart from age. Interestingly, there's some other ways of doing it. These are called QQ plots. And the idea is, if it is normal, then all the circle dots, all the plot points, should be as close to this straight line as is possible. So as you can see there, the QQ plot is not the best, and if we look at stature, that is very much more on the line. Of course, there's one outlier there. With mass, same thing. So QQ plots are very good as well. But also what you can do is you might slightly see little waves here, like it kind of starts underneath, goes up and down again like that, a little wave. In the mass, something slightly similar, and in age, it's like a kind of a hill going up and then down like so. We can use this to kind of describe it slightly differently as well. So there we are. That's the descriptive analysis done, and what we've identified is that the data that we're going to be analysing is normal apart from age, but we're going to just take that as normal for now, because we'll change the title to say undergraduate students in a little bit. So now, because it's normal, that means there are certain tests that we can use. For example, if we're using normal data, we can do correlation tests to see if there's any similarity in it, and also later on we'll do a test to compare the means. Is there any difference between the Margaria and the Wingate test? But let's just go to graphs first of all. If I click on Chart Builder, let's have a look at some of the things that we can do. So what I'm going to do is I'm going to just create a scatter plot. So I'll click on scatter. We'll go for this simple one here. Now what I want to do is we're going to put the Wingate watts per kilogram there, and we'll start off with the sergeant jump here. So I'll stick that there. If I click on OK, we should get this graph here. And the question is the sergeant jump comparable to the Wingate test? If it is comparable, then what you should find is all those plotted points should be on a straight line. If I double click on here, what I can do, I'll just change it slightly by just sticking in a line of best fit. And what I've done there is the computer's just worked out what is the best fit line for all these dots, and now we can actually see if that's the line of best fit, how close are these dots to that line. And as you can see, it doesn't look like there's going to be a strong correlation. So sergeant jump, is it a cheaper way of doing the Wingate? At the moment it doesn't look like it, because whatever result you get in the sergeant doesn't really correlate with what you get in the Wingate. Let's have a look at a different graph. Let's compare the Margaria stair test now instead of the sergeant jump. So if I click on this one here and stick it in there and click on OK, what we got now is this, and already you can see, well actually it is starting to form a line. I'll just make that a little bit better by sticking in a line of best fit with this one as well. And as you can see, there's a line of best fit, and they're all a lot closer. So maybe there's a possibility that we don't have to spend £5,000 on a Wingate, and we can actually use the Margaria, which will then help us because we can go out into the field and do it instead of sending everyone to the lab. So there's a little bit of a possibility. So what I can do is, visually again, it looks like there's a strong correlation between your results for the Margaria and the Wingate. Let's have a look at it statistically. Let's do a test. So what we can do is, if I go back to the data, instead of doing graphs now, what I'm going to do is I'm going to statistically analyze it, and on here is an option correlate. So I'm going to choose a bivariate correlation, a Pearson bivariate correlation, because the data is normal and it's of that kind of ilk, and I'm going to test, well, let's do them all again. So let's do the sergeant jump. We've got the Margaria and then the Wingate, two-tailed, which means it's normal shape both ends, and if I click on OK, what we should get are some little values here. Now these are correlation values. We talked about this earlier, but with a Pearson correlation, if it's a value of 0, then that means there's no relationship between one against the other, and if the score is 1.00, there is a complete association with one to the other. So the closer to 1 we get, the better we can say there is a link. So for example, with the sergeant jump compared to the Wingate test, it is 0.168, and as we saw in the graph, it was pretty scattered, and this is backed up with this value here. It does look like there is not much correlation there, but if we look at the Margaria stair test compared to the Wingate, it's got a value of 0.862, which is getting quite close to 1, so that's pretty good. Now to help us here, what we have is another sig value, and if that sig value is below 0.05, then we can say there is a significant correlation. So here 0.454 is well above that, so we can say there's no significant correlation between sergeant jump and Wingate. But if we look at the Margaria, then here we've got a value of 0.00. Instead of doing the Wingate, why not just do a Margarita? It'll give you a similar result, then you can work out who is faster than the other. So there is a correlation there. But if we go back to the Excel spreadsheet, we did say that the mean score for the Margarita was 14.71, whilst the Wingate was 13.58. So yes, if you score low in one, you'll score low in the other, and high in one, high in the other. But there does seem to be a little bit of difference here. Yes, was it 1.13 that we said there was a difference? It does seem quite big, but what we can't say is whether this is a significant difference. So there is another test that we can do, and this is a t-test. The t-test will have a look at all the data and say, are all the numbers from one pot of numbers, or in other words, they're all a bit of a mishmash, or are they two separate entities? And if they are two separate entities, we can say yes, there is a significant difference between one compared to the other. So going back to your data, what I'm going to do this time is click on Analyze, and then I'm going to choose Compare Means. And the test I'm going to do is a paired sample t-test, which basically means for both tests, each subject did each one, and also the data's normal. So that's what we're going to use. And the two things that we're going to look at are the Margarita, watts per kilogram, and the Wingate, watts per kilogram. Just check the options. Yep, it's 95%. As I say, that means if we did this test 100 times, 95 times out of the 100, we'll expect to get the same results as we will do today. And I click on OK, and what I should get here is a value. For starters, it will give us the mean values and standard deviation, so straight away you can say, yep, there is a difference there. And then the correlation that we've done before, 0.862, which seems pretty good, and the sig value of 0.00 means there is a strong correlation, so things are looking pretty good up to now. And then these are the t-tests, and the key value here is the sig value at the end. If this is less than 0.05, then we can say there is a significant difference. And as you can see, 0.01 is less than 0.05, so there is a significant difference. In summary, what we can say is the Sargent test doesn't seem to correlate well with the Wingate test, so it's not a good substitute for it. It is measuring power, but it seems to be a different kind of power that it's measuring. Whereas the Margarita test and the Wingate test do produce comparable results. One does compare with the other. However, the Margarita test does measure a little bit higher than the Wingate. So that, in summary, is what we have found from our stats. So you need to kind of interpret this and apply it into your assignment. What I'll do is I'll create some more resources to help you with this. Thank you very much.